Hello everyone and welcome to my presentation. My name is Reza Farahani, PhD researcher at University of Klagenfurt, and today I'm pleased to present our recent work entitled ES has an Edge and SDN assisted framework for HTTP adaptive video streaming. First, I will introduce HTTP adaptive streaming technology and some modern networking paradigm that we used in this work. Second, I will present one of the state-of-the-art approaches called SABR. Next, I will present our motivation by an example. Then introduce our framework in detail. Then I will describe our evaluation setup following experimental result. And finally conclude the presentation and talk about some possible direction for future work. As you know, video traffic has been become the dominant traffic over the internet, and according to Cisco Visual Networking Index (VNI), it is expected to reach more than 82% of all internet traffic in 2021. HTTP adaptive streaming, or shortly has been considered as the de facto video delivery technology over the internet. As you can see in this figure, the whole video is divided into a small chunks or segment, then encoded into multiple bitrate or resolution called the representation, stored in the origin server or cache server. Then video players adapt the video quality by considering client resource, I mean the payload buffer or network condition. What is the challenges in has domain? The adaptation process can be performed with different scheme. One of them called pure client base. In pure client base approach, the adaptation decision based on the local parameters like buffer status, estimated available bandwidth, or hybrid of them. So pure client-based approach has insufficient information about the network. Then it could lead to a suboptimal adaptation decision. In another way, network-assisted video streaming is introduced. In the network-assisted adaptation, the adaptation decision in the network assisted approach is performed via a centralized network component with a holistic view of the entire network topology. So this approach can be more beneficial for the user's QE in comparison the pure client base. Fundamental paradigms of a modern network mean SDN, NFV, edge computing, fog computing have been used in modern network assisted framework. But what is the software defined networking paradigm? This paradigm is considered as a fundamental paradigm of modern networks like 5G to address the limitation of traditional network problems like complex network devices, management overhead, or limited scalability. As you can see in this figure, the data plane and control plane of the traditional devices like router or switches are decoupled in the SDN manner, and the control plane are located in a separated layer called control plane layer or SDN controller component. So thanks to the SDN control component, we have a central management of the network in the SDN approach, and we can define our desired application like monitoring, traffic engineering, routing algorithms, etc., in a management plane top of the SDN controller. Also, we can communicate with the dummy devices that are responsible for forwarding the traffic in the data plane layer with the control plane. So we have centralized network control, standard communication interface like OpenFlow and programmable open APIs in the SDN network. But there is another technology called NFV that is considered as a complementary technology to SDN. NFV enable virtual network function or VNFs like virtual network function, routers, virtual network function, firewall, load balancer, or switch run over an open hardware platform instead of vendor-based like a Cisco or Juniper firewall, load balancer, etc., etc. So we can reduce OpEx and CapEx cost in this approach and accelerate innovation by having VNFs and NFV technology. Let's talk about one state-of-the-art called SABR as Network Assisted Content Distribution for Adaptive Bitrate Video Streaming. In this paper, the authors modify the code of Dash clients to receive some information from the SDN controller, I mean the available bandwidth and cache occupancy, and by this information client could decide about the next segment precisely. But what is the challenges in this type of network assisted system? Imagine a simple scenario with just two dash client, two open flow switches, an SDN controller, and one cache server. We try to show the number of communicated messages in this system by HTTP messages and open flow messages. Uh, for each client, we should request to receive the desired information like cache occupancy, also available bandwidths. So if the number of dash client increase, the number of exchange message to from the SDN controller increased as well. So the system efficiency potentially decrease. And this is the main issue in this system. For addressing this issue, we propose ESHAS as another network assisted system. ESHAS uses the virtual reverse proxy server or VRP at the edge of the network. We define this component by NFV technology. So VRPs plays the role of the gateway for the client to the network and vice versa. Each dash client send its request to the virtual reverse proxy for the desired segment quality, and virtual reverse proxy collect a number of receive requests in a time slotted fashion. So the virtual reverse proxy requests the cache map and network and status information from a SDN controller for all collected requests, not for each request. And in this step, we could decrease the number of communicated message to the SDN controller. So finally, the VRP determine the optimal cache servers for the gathered client requests. If we take a look at the previous scenario by adding one virtual reverse proxy and investigate the number of communicated message both for both OpenFlow and HTTP messages, we can see the number messages to or from the SDN controller will decrease in ESHAS system. In ESHAS architecture, we have three different and separate layers. In application control layer, we place this SDN controller. Also in the network core layer, we have multiple cache servers that can communicate cache map information to the virtual reverse proxy. Also, we have dummy devices like OpenFlow switches just for forwarding the traffic. In the third layer, we place our virtual reverse proxy in this layer that includes server service optimizer module or SOM and request analyzer module. Request analyzer module in our virtual reverse proxy works in the first parts of our considered time slot. So in this part, our VRP tries to collect some information from the network. I mean the cache occupancy or cache map and available bandwidth. Also the client request. So you can see we just send one request instead of bunch of requests for each client for the mentioned information. And in the next Next section of the time slot, we run our optimization model to find the best place for fetching the requested quality. By this approach, we can serve all clients' requests and just send one request instead of bunch of requests for the required data, also for the repetitive clients' request. As another novelty of this paper, we introduce server segment selection policy. In the cache hit situation, I mean the requested quality level exists at least in one cache server. We can find the best cache servers in terms of the fetch time and serve the client's request. But in the cache miss situation, we can use the new concept, replacement quality, that defined as a better quality instead of original requested quality, and serve the client with the replacement quality, or use the original requested quality like traditional approach and SABR. So the objective function of our optimization model is minimizing the fetch time, also minimize the deviation when we use the replacement quality. The deviation means the difference between the replacement quality and the original quality, also the maximizing the bitrate level. For the evaluation, we use the large scale and cloud-based environment in the Cloud Lab testbed, including 60 client, 4 cache servers, 1 origin server, 5 OpenFlow switches, and SDN controller, 2 virtual reverse proxy with mentioned modules that implemented via Python, and pulp with CBC solver, a video dataset including 10 video sequences with different segment lengths and 5 representation, 2 different ABR algorithms as a hybrid and buffer-based ABR algorithms, etc., etc. You can find more information in the paper. In the evaluation parts of the ES we firstly analyze the behavior of our optimization model by adding the number of cache servers, also the number of segments requests, and measure the execution time of our optimization model. As you can see in this figure, the execution time will increase when we increase the number of cache servers, also number of segments, and we measure the value of the time slot duration for 2 seconds, 4 seconds, and 6 seconds in this experiment. You can find more information in the paper. As another part of analytical analyze, we analyze the impact of different parameters on ES MILP model behavior by defining 3 different metrics: ACS, AMD, AQB. If we take a look at the optimization objective function of our optimization model, we consider the fetch time, also the deviation and quality. These metrics are correspond to the fetch time of the best cache server, also the deviation and quality, and everything according to this table. Everything was according to our expectation. By changing the value of weighting parameters in the optimization model, we could fetch much more requests from the best cache server. Also uh, use the deviation replacement quality with deviation or not, and um, higher quality in the cache miss situation. We needed to investigate the behavior of ABR algorithms in reaction with the replacement quality. As you can see in this figure, in both ABR algorithms, the performance of The overall performance of ABR algorithms didn't change and didn't destroyed by overwriting by replacement quality. Multiple time we encountered the replacement quality, for example, here and here, but as I mentioned, the performance was acceptable for us. Our framework could outperform traditional approach, I mean pure client-based and SABR in terms of number of received, number of requested per quality, and highest quality, also the playback bitrate. Also, we could decrease the average number of stalls and the average number of quality switches. As a conclusion, we leverage the SDN and NFV and cloud and edge computing, cloud and edge computing to propose ESAS as a network-assisted video streaming framework. We introduce component named VRP, and we also introduce a new server segment policy. We implement our approach in a large scale testbed consisting of 60 clients and validate our approach. The results are shown that our approach could outperform state-of-the-art also SABR and traditional approach by at least 70% and 40%. Edge caching, edge collaboration, and extending proposed MILP model and learning-based approaches, meta-heuristic, are possible future work direction. Thanks for your attention. I will be happy to answer your question.